Hello, everyone. Welcome back to the Topos Institute Colloquium. Today, we're very happy to have Mohamed Barakat talking to us about CAP, a categorical reorganization of computer algebra. So, Mohamed, whenever you're ready.
Thank you very much. Thank you for the invitation and for your interest. This is my second talk at the Topos Institute. My first talk was at the Berkeley Research Seminar, and I might be referring to it during my talk, so please feel free to interrupt me at any point. So not just clarification questions, but any questions you might have, and then I can stop and then we can discuss. So let me start. This is joint work with members of our working group, Sebastian Poser, Kamal Saleh, and Fabian Sigraf, and Tom Kuhmichel. So a lot of ideas in this talk are really born in the thesis of Sebastian Poser and his subsequent work. Kamal implemented triangulated categories and derived categories, and Fabian is the architect of the compiler, to which I will say something towards the end. And Tom is a recent PhD student, and he really developed the monoidal stuff in CAP and is currently active in building yet more categorical towers that you will hear about during the talk. So let me start. I'm actually a computer algebraist, and we had a computer algebra project that we started several times, and now we're actually happy that we converged towards a categorical understanding of everything that we're doing, and this is really a game changer for us, and I hope this will become more and more apparent in the talk. So let me start by a motivating application that we had in computer algebra. So in this application, we wanted to compute the space of solutions, which I denote by sol of delta, of smooth solutions of the linear PDE system that you see there. So this is non-constant system. You see here the x's popping up. So it's a nonlinear PDE. So it's a linear PDE system with non-constant coefficients. And you see there you go up to degree 3, and this is a PDE system in three indeterminates, namely x, y, and z, and two unknown smooth functions, f and g. Okay, and we call the system delta of f and g. So this is something that looks like analysis, but we want to gradually turn it into computer and then tackle it with computer algebra methods. So the first step towards an algebraic approach is to somehow recognize that there is a ring of differential operators called the Weil algebra, and here we take polynomial coefficients. Of course, you can think of Weil algebra as having even analytic coefficients or other sort of coefficients, but we just take polynomial coefficients. So this is an over domain, and it has a Grosvenor basis theory. So now we see that our system can be encoded as an 8x2 matrix over this Weil algebra in 3 indeterminates and 3 partial derivatives. And this 8x2 matrix is then applied to this section. So this section, this unknown section is a vector containing 2 unknown functions f and g, and we want to get 0. So this is just the passage from this system here unstructured to a matrix approach. Okay, I think this is an easy step. You see I have here 2 columns because I have 2 unknown smooth functions that I would like to compute or determine in full generality. Yeah, and this space of smooth functions is actually a D module. And this will bring me already to the next step. So the next step starts with generalizing the problem. So let D be the n-dimensional Weil algebra, M delta a matrix over D, a P by Q matrix, and F the D module of smooth functions on n indeterminate variables, x1 till xn. So the n is the same as x1 till xn. And the system, the PDE system can now be encoded as m delta times psi, and psi is a section in f to the q. So it's a vector having q smooth functions. So then we can interpret the matrix m delta as a morphism of free D modules. This is the somehow apparent thing to do if you have a matrix and you look at it as a map between free modules. And why do you want to do that? Because we're interested in its image. And its image is actually encoding all the consequences of the rows of m delta. So you see, this is nothing but the space of linear combinations of the rows of m delta. So in some sense, we want to work with the differential equation, or the 8 rows of differential equations, or all rows of differential equations. And in some sense, we want to work with them as if they are satisfied. This is why we go to the factor module. Okay, so we want the system to be our 0, right? And as you know, this is nothing but the co-kernel of the map. So this system module m delta is nothing but the co-kernel of this map. It's a map between free D modules. And the residue classes E1 bar till EQ bar of the standard basis of the free D module, D1 cross Q, now interpreted as elements in the factor module or in the co-kernel, is a generating system of m delta with a very nice property that the rows of m delta of the matrix are the defining relations between these generators. So in some sense, we have m delta times this generalized section is equal to 0. And m delta is not just any matrix, but it's the defining matrix of relations, right? So we therefore call this vector of abstract vectors the abstract solution of the system, right? It fulfills the same equation as the section of smooth functions we're looking for. So this means when we want to define a D module morphism between m delta and f, this means we have to find images for the abstract generators. But since these abstract generators are not free, they satisfy relations, the images must satisfy these relations. But what are the relations that the EIs are satisfying? They're satisfying the m delta, right? So this means the images must satisfy the m delta. So this means the images are actually solutions. And then we get a map from Hom m delta f to the solution space of delta with values in f, which is an isomorphism of R vector spaces, right? So this is a more or less a set theoretic understanding of what's going on. But the nice thing is that at some point, category theory will help us develop yet another understanding of all of this. So this lemma implies that, so this lemma is, by the way, due to Noether, and it was rediscovered by Malgrange. This lemma is telling the solution space only depend on the isomorphism type of m delta since it's actually a Hom. So if you insert in Hom in the first argument another isomorphic module, you'll get the same solution space, even if the other module is generated by a different number of generators. So the D module m delta can be studied then independent of the solution space. So, and then you can say, actually, I now want to study polynomial solutions or rational solutions or smooth solutions or formal power series solution or whatever you like. Yeah. So somehow you subdivided the problem in 2 problems. First study m delta and then decide where you want to find the solutions, right? And a different generating set of m delta yields an equivalent system, delta prime of linear PDEs, with m delta actually equal to m delta prime if it's just a change of generators and you didn't physically change the module set theoretically. But in general, you can also think of another isomorphic module m delta prime, right? So given a finitely presented D module M, there is something called the bidualizing spectral sequence. It's a double X spectral sequence that converges for this combination of dimensions, or in this case, codimension P and Q, to the module M. And this spectral sequence doesn't not just give a grading, but it gives rise to the so-called purity filtration of M. So this double X spectral sequence is algebraically definable for so-called Auslander regular ring, and the Weil algebra is Auslander regular. But of course, if you think about it, what it would mean in terms of commutative rings, so just polynomial rings, then this filtration has a very nice interpretation. It's just the filtration of the module by equidimensional graded parts. So you're going to have a filtration, and every part in the filtration is a pure part. So it has the same codimension. So you can use this filtration to solve the above linear system. And here I would like to show you what we did with our previous software. So I have loaded the necessary software. Modules is part of the Homalg project. It's not yet in CAP, although huge parts of it are now moving to CAP. So now I read the file called Weil, and everything is now running in GAP, and I'm just using Julia as a front end just to be able to work in Jupyter. So this CAP and Homalg is just a very thin layer in Julia, and it's actually communicating with CAP. But apart from that, CAP is already in Julia in a more native way that maybe we can discuss about in the question sections. So now I display the module M, and this is exactly the matrix that I showed you. So let me go back to the matrix here. So this is just this matrix. Okay? And now you see that M is the co-kernel of this map. And F is the injective module of all smooth functions in Maple. So now I'm communicating with GAP, which itself is communicating with Singular for the Grosvenor basis engine. But on the other side, I'm communicating with Maple to ask Maple to solve PDE systems. And now with this system, I'm simply asking Maple to solve it. And you will see that Maple takes some time and then gives me a completely unusable solution. So it tried an ansatz and basically it failed. Yeah, you see here the integrals. So I still need to do integration. And now I do this filtration, which is induced by this bidualizing spectral sequence. And these are Grosvenor basis computations happening in the background, but they are somehow informed by algebra. And now if I display M, so M had a side effect by this computation, and it changed in place. So first of all, you see that now the matrix of relations is now not an 8x2, but a 6x3 matrix. So even the number of generators changed. So from 2 generators to 3 generators, and the number of relations changed from 8 relations to 6 relations. But the wonderful thing is that you already see the triangular structure here, right? And now this is just to prove to you that there was a spectral sequence computation happening in the background, depending on if you understand what a spectral sequence is. This is the rate of convergence. So the first spectral sequence collapsed. So it's a bicomplex spectral sequence. The first one collapsed on the second page, and the second one also collapsed on the second page. And this is the grading. The first one collapses to M, to the module M, and the second one collapses really to the filtration, giving you the graded parts on in each grade. So now we can compute the space of solution with regard to this new set of generators and this new set of relations. And if we compute Maple, if you've noticed, comes back much quicker. But now I have 3 generators. So I'm solving for 3 other smooth functions. Let's call them not F and G, but U, V, and W. And now I can display them. And you see that the general solution depends on a constant, depends on a function in one unknown and a function in 2 unknown. And you see here that the constant is entering at two places, the function in one unknown is entering in two places, and the f2 in two unknowns is just in one place. But the nice thing is that we can simply jump back. So we can tell the module, please go back to your original presentation. So you see here it was on 6 relations for 3 generators. But if we jump back to the original one, it will go back to 8 relations for 2 generators, but it gained knowledge. So now it knows that it's non-pure of grade 1 left module, blah, blah. And the solution space knows about is somehow connected to the module. So if you display it, now you see the 2 solutions, F and G. So this is F, and G is longer, which is just on 2 lines. This is the Maple output. And this is the stuff that Maple was unable to solve in the first place. Yeah. So now with an algebraic pre-manipulation, you could help Maple to put a system in a form that it could easier solve. So this thing is academic, so that it's not really something that comes from application, but the systems that come in application are systems from linear control theory. Yeah, I'm just taking something where you see that the spectral sequence is a bit more complicated and the system is complicated and higher order and so on. Okay, so let's go back to the slides. Any questions so far? So computing spectral sequences and their induced filtrations required computational models for the abelian category of finitely presented D modules. Let's call it DFP mod, and diagram tracing in abelian categories. And both were realized in the Homalg project. This is the project which, the one that preceded the CAP project, the one which we're working on right now. And in that project, the FP mod was implemented as an abelian category. The only modular part of the implementation was the ring D. So in our application, D is just, it was the Weil algebra. And depending on D, the implementation required various normal form algorithms. So if you start with D a field, then you need the Gaussian algorithm. So the Gaussian elimination. If you take D equal to Euclidean domain, then you need the Hermite normal form. And then you go to Grosvenor basis all the way up to non-commutative Grosvenor basis if your ring is non-commutative and allows for a non-commutative Grosvenor basis algorithm. And diagram tracing was realized by something called generalized morphisms, which we now also have in CAP. So if you have questions about these generalized morphisms, we can talk about them at the end, but the idea is fairly simple. When you want to do diagram tracing, as you will see in the example, sometimes you're going downstream, but in the next step, you're going upstream. So in some sense, you would like to invert a morphism, which is not invertible in the category of abelian groups. But what do you do? So you go from in simple words, you go from functions to relations. So you go from morphisms in an abelian category in relations in an abelian categories. I think some people call these allegories. Some people call these correspondences. These are known in also this correspondence between what I call generalized morphisms and relations is known in group theory as the Gorsal lemma. So it's have been discovered several times. Yeah. So Homalg was actually well designed for the intended application, however, not modular enough to cover more applications. And implementing more complicated categories become increasingly difficult, not to say a nightmare. And generalizing from finitely presented modules to coherent sheaf, for example, was a pain. We managed to do that, but it wasn't an easy exercise. So the remedy would actually to take category theory more seriously, which we did with the time, but somehow we needed this level of pain to really come to the conclusion that we have to take category theory seriously, not just to implement category, but also to use category theory as a guide for all design decisions, not only the important ones. and make categories, functors, etc., natural transformations, and whatever. They should become first-class citizens and turn category theory into a programming language in the sense that we should write all programs just using the categorical vocabulary in the sense of really exclusively. Yeah. So what does DFP mod categorically? So then you can actually, so D is a ring, so it's not really something that you think about categorically, but it's actually a k-linear category on one object. So this is the very modest start. And then the category of finitely presented modules over the ring D is just the finite co-limit completion of D. Yeah. And as such, you can actually realize it in two steps. So you could first take, when you start with any k-linear category, so this is something which I'll call a doctrine on the next slide. So if you start with any k-linear category, you can take its additive closure. And the additive closure is just the left bi-adjoint to the forgetful functor from additive categories, so or k-additive categories. These are categories with direct sum. And if you forget the direct sum, then there is a left adjoint that gives you direct sums in a universal way. And the next step is really to go from categories with direct sums to categories with direct sums and co-kernels. And this is already enough to give you all co-limits, right? So co-kernel is then the linear version of co-equalizers. And if you have co-products and co-equalizers, you have all co-limits, right? And this construction was introduced by Fried. And the additive closure formally adds direct sum, and it's actually the place where matrices are invented. So if you don't know anything about matrices, and you think about how to find a left adjoint to this forgetful functor, you will end up inventing matrices. And Fried is formally the construction that adds co-kernels. And it's, if you want to model it, it's just a quotient, a certain quotient of the arrow category. So it's very easy to implement. If you have the arrow category constructor, then you just, and the quotient category constructor, then you compose both, and then you have Fried. So even Fried can be written as a composition of two things, right? So the above tower of categorical constructors is typically composed of several free forgetful two adjunctions or bi-adjunctions in general, because the zigzag identity is usually not strictly fulfilled. Between a two category D of categories, so they're called what we call doctrines, so D for a doctrine, and another doctrine E of categories with extra structure. So you can think of D as being K-mat, K categories, so K-linear categories, and E of being K-additive categories. Yeah, or you can think of D being, I don't know, pre-abelian and E being abelian categories or something like that, right? Yeah, so you want to add one more structure. And then the question is this an adjunction? So here is a software demonstration again. So here I show you how the category of finitely presented D modules can be constructed. So this is Q. Q is living actually in singular, the field of rationals. And in singular, the Weil algebra is implemented. It's implemented in a package by Victor Lewandowski called Plural. It's a subsystem of singular. And here I'm taking left presentation as Fried category of rows. Yeah? Category of rows is just the additive closure of the ring. Yeah, it's another name for this. And so here it's just telling me I'm the category of left presentation, so the category of finitely presented modules. But if you look at the modeling category, you see really it's Fried of rows, and rows is the additive closure of the ring as category of the Weil algebra. And if you display this, you see that it's telling about itself that it's actually an abelian category. So if you look at the doctrines we currently have in CAP, so this graph has something like 82 nodes. You start with a category. So let me show you where is abelian here. So here is pre-abelian, here is abelian, and it comes from an app category And it goes back to enriched over commutative regular semigroups and so on. And down here, you see the monoidal stuff. So is a monoidal category, and then closed and co-closed and symmetric and rigid and so on until you end up with lattices, right? Okay, so let's go back to the talk. So the dual category construction is also a two-adjunction on each doctrine. So this means we could also use it in the same manner, and it also has really a unit and a co-unit, which played a role in my Berkeley seminar talk. Today it will actually play no role. So there I used the unit and the co-unit really to extract algorithms out of the tower itself. And implementing the opposite category requires a lot of meta programming, as you probably know from developing CATLab. And the problem is that the system is evolving, so you're adding more doctrines and so on, but the opposite category constructor is fixed. So you want somehow that every doctrine you're writing knows about the existence of the opposite category constructors and informs it, so that when you have a new doctrine, that the opposite category knows about it and behaves well with it. And once you have the opposite category, you can, out of the fried, which is formally adding co-kernels, you can now formally add kernels by just composing opposite pre and post. You can also get the finite completion by saying it's the opposite of the finite co-completion of the opposite. And the finitely presented co-presheaves are then the opposite of the finitely presented presheaves of the opposite. Okay. A longer categorical tower of bi-adjunctions yields even the abelian closure as a categorical tower of two adjunctions, and where you could start with the linear categories and go all the way up to k abelian categories. But you could even start lower by starting from quivers and then take path category as a left adjoint to the forgetful functor that takes you from categories to quivers. And then you can start with categories, and then you can take the linear closure. So this is the name of the linear closure, which you will see on the next notebook. And it is left adjoint to the forgetful functor that takes a linear category and forgets its scale-linear structure. Yeah. So here's the simplest diagram chasing. So going back to the example, to the motivating example. So this is something that you also saw in my first talk, but here the emphasis will be on something different. So the snake lemma is somehow the simplest diagram chase you could think of. So the setup is given three composable morphisms, A, B, and C, between object capital A, capital B, capital C, and capital D, in an abelian category satisfying the relations that A times B times C is equal to 0. Right? So now you can take the co-kernel of A, and since B composed with C is a competitor for the co-kernel projection, because ABC is equal to 0, there is a co-lift. And then you can take the kernel embedding of E, and dually you can take the kernel of C, and since A times B is competing with G as with the kernel embedding G, because A times B times C is equal to 0, there is a kernel lift H, of which you can take the co-kernel. And then the snake lemma tells you that there is a snake going all the way from the kernel of E to the co-kernel of H. And this thing is essentially unique natural morphism from the kernel of E to the co-kernel that satisfies even more conditions, namely that if you compute J and K, which are the functoriality, so this guy is just expressing the functoriality of the kernel, K is expressing the functoriality of the co-kernel, then you get this exact sequence. Okay. So here is the next software demo. So I'll run this notebook twice. Once with I'll use two different towers. One of them is not compiled, one of them is compiled. And I want to show you the difference. So here is the setup. I have I start with the quiver, as you saw on the previous slides, that you can really start at the bottom. So here is a quiver of free composable morphisms. This is the path category or the free category. And if you display it, it just knows that it's a finite category. It knows how to compute external Homs. And now you linearize the category. So you take it, in this case, over the rationals. We could have taken it over the integers so that we get the full statement. And now we linearize. Now we say that A times B times C is equal to 0. And we display L, and we see now the category knows about itself that it's actually linear, not just a category. And then we do the leap to the abelian closure. And now I'm taking as abelian closure the tower that is using the Fried of the co-Fried of the additive closure of L. So the additive closure adds you direct sums. So these are products and co-products, and the Fried adds, and the co-Fried adds formally kernels, and the Fried adds formally co-kernels, as I just mentioned. So if I execute A, you see it's just telling about itself. I'm this. And if you display it, you see that it's a category which knows about itself, that it's abelian, even with enough projectives that we won't need the projectives, but the category knows enough about itself. It can compute external Homs that I used in my previous talk. And the underlying category is indeed this linear category. So the modeling category of this, as I told you, is really the Fried of the co-Fried of the additive closure of the algebroid. And let's get this co-Fried out. So this is L brief. And this is actually the co-limit completion of this algebroid or of this linear category. And how's this guy modeled? The co-Fried is really modeled as the opposite of Fried of opposite, as I just told you. And now we go and upgrade our morphisms in the quiver to morphisms in our abelian category. So this is a successive UNADA embedding, if you like. And now in the abelian category, the composition of these three morphisms, thanks to the relation I just plugged into my linear category, is indeed 0. So now I can do everything I did on the slides. I can now take the co-kernel D, and then I can take the co-lift, co-kernel co-lift, and then I can take the kernel embedding, and then I can take the kernel lift of the kernel embedding. Then I can take the co-kernel projection, and now I have everything. So now I would like to do the snake. And how does the snake go? It tells me downstream, upstream, downstream, upstream, downstream, right? So first of all, I need to embed my morphisms in the appropriate category of relations, yeah, because I can flip relations. So these are the so-called generalized morphisms. As I told you, this was already understood by Gaussen, that the generalized morphisms are nothing really but the relations. And so now we change the category and go one level higher in the tower. And now we have all of them, which we now can pre-compose exactly as we intended. So this is F. This is the pseudo-inverse. So FF is F regarded as a linear relation, right? DD is now D regarded as a linear relation, and so on. And now if we pre-compose downstream, upstream, downstream, upstream, downstream, we get, again, a relation, but this relation is actually honest. And now this computation is in a tower which I deliberately did not compile. And this takes something about 20 seconds.
So you're checking that it's a function, a morphism.
Exactly.
Yeah, not
it's an honest
generalized.
morphism. Absolutely, yeah. Okay, so now here's the honest representative, and you can see that it fulfills the stuff that we actually wanted from it. So I computed J, and I computed the homology object at this point, and I'm just verifying that the homology here is 0. So at this point, this sequence is exact. So let me compute also the K, which is this guy. So let me compute K and check that the homology at this object is also 0. Yeah. Let me go to the next one where I have another tower. So the other tower is now using, instead of fried, of co-fried, of additive closure, it's using pre-sheaves. And this tower is compiled. So let me show you the difference. So I'm just going through it. So now I'm taking abelian closure. Where is this? So this here, and it's just using a different model. So if I display it, it's still abelian, even with enough projectives. The underlying category is still the thing. If I look at the fried, at the modeling category, it's the fried of the finite completion. And what is the finite completion? It's the modeling category of the finite completion are the co-presheaves, and the co-presheaves are again modeled as the opposite of the functor category, and the functor category is the presheaves composed with the opposite, which is awkward. Usually, you have the functor category as the basic thing, but we decided that actually the presheaves are actually the basic thing, and the functor category is defined as the presheaves composed with the opposite. And now you do the upgrading again, and now I'll just, this is exactly what you saw. The only difference will be checking that the honesty. So here it's the same. Okay, now this took 20 seconds, and now this is more or less immediate. So it just has a small hiccup because not the entire tower is compiled, but part of the tower is compiled. So now you can extract the honest representative and then do the same again, yeah, and then compute the homology object and so on. So now this is the connection to my previous talk. So that actually you don't even need to come up with the idea of these generalized morphism. If you want to prove the snake lemma, now we have a free instance, which is the free abelian category on this context, right? Three morphisms satisfying A times B times C equals 0. And actually using this, we proved that there is such an S, but there isn't even a better way to prove that this S is essentially unique by simply computing all morphisms in this free abelian category from this guy to this guy. And if you remember, our abelian category was able to compute external homes. So let me go back again. Where is A? So A is able to compute external homes. Right? So now we can go and compute the kernel and the co-kernel. So these two objects. And now I compute a basis of the external home, in this case, a Q basis, because I'm working in Q linear categories. And you see there, this list had just one element. And now I can check that the snake that I constructed by going up to the generalized morphisms and doing this downstream, upstream, downstream, upstream, and so on, is something that I could have simply found by asking the free instance of this context, how many natural morphisms do you have? And it just gave me this as, of course, just scalar multiples of this, but it happens even to be that the basis element is exactly the snake that I constructed using the previous approach. So that's all about the Jupyter notebook. So then we're turned to the slides. So exercise along the same lines, treat spectral sequences of Y complexes. So then you don't have just ABC, but you have such a thing. And then you take the quiver with which you encode these things so that this is a complex, that this diagram, that these squares anti-commute, and you put all of them in the relations. And then you can really compute the spectral sequence. So you can take the vertical things, compute homology, and then you can take or cohomology, and then take the horizontal things, horizontal maps, and then compute homology, and then take these guys, and then ask the system how many morphisms do you have from year to year, and then it just tells you there is only one. Yeah, and it really gives you the map, the generic map on the second page of a spectral sequence. Yeah, and I did this exercise, and you can really extract the algorithm to compute the second morphism of a spectral sequence in an arbitrary abelian category of a spectral sequence coming from a bicomplex, right? So you don't even need to understand anything about this. You just write down the setup and then ask the system. So give it the setup, say I want the free abelian category on this, and then give me this morphism. Okay, so we can actually model a lot of stuff. So C is then, R is a ring, and C is the process of viewing a ring as a category on one object. So this is somehow categorifying algebraic objects. So what is the free left R modules? This is the ring viewed as a category and then the additive closure. And the free right modules is just the opposite of this. The finitely presented is left modules is when you do the fried. So this is the co-kernel completion. The finitely presented right modules is when you do the fried of this op. The quivers are the functions or the presheaves from this quiver into sets. The ZX diagrams can be a subcategory of the cospan category of some slice of the category of quivers. And the free abelian category is what you saw. So you saw it as the fried of the co-fried of some additive closure. So there is a plus missing here. And linear representation of groups over a field are just some functions from the group regarded as a category into the skeletal model of the K-vector spaces. And even when you want to do algebraic geometry or affine algebraic geometry, and you want to have a model of the radical ideals of a ring, not just the ideals, but really the radical ideals, without having an algorithm to compute radicals, then you can do this completely category theoretically, and this is really nice. Yeah, so this is a model that doesn't necessitate to know how to compute radical ideals. And still you can compute with the poset of radical ideals. So the advantages is reusability. So here you see how often I'm using the additive closure in these different applications and how often I'm using the opposite. So there is actually one plus missing here. And I used fried several times. I used the functor category several times, or alias presheaves. I used the slice category several times. So building blocks can appear in multiple different contexts. And this was our nightmare in Homalg, that our modularity was too coarse, right? So coarse-grained. We just had this fantastic, very fast computing category of finitely presented modules, but apart from that, we had to write everything from scratch, and things really got very complicated with time. But now the nice thing is that we have a separation of concerns, so focus on a single concept at a time. So focus at what is a slice category, what is a fried category, what is a poset. So a poset means that you take your category and slash all morphisms to be one morphism. All parallel morphism are identified, right? And now you can verify this by just either going through the code or using a simple-minded proof assistant that we have in CAP. And the emergence, as David, I don't like the word, but I hope that now it's somewhat substantiated, that the whole is really greater than the sum of its parts. That somehow this here doesn't know that it will model the category of ZX calculus eventually, right? Or this here doesn't know that it will give you a model for free abelian categories, right? So here you see really the components knowing nothing about what will emerge at the end, right? So I hope this is much more substantiated than the colloquial use of the word emergence. So the effects on computer implementation, you have efficient development thanks to reusability, separation of concerns, verifiability, and emergence. But there is a culprit, and namely the inefficient execution due to computational overhead, right? And you saw two different towers. One was non-compiled, one was compiled, and you saw the difference, something like a second compared to something like 15 seconds or 20 seconds. So the solution is really compilation. And somehow you have this already in Julia because CATLab is written in Julia. But let me articulate it a bit more. So actually, we're very happy to have started in GAP. So in GAP, we reached this pain level very quickly, right? Because GAP is an interpreted language, unlike Julia. And so GAP forced us somehow to develop the compiler, right? Because everything is then interpreted over and over and over again, and the boxing and unboxing that you will see was not done by anything, but it's really done by the interpreter and so on. But once we started developing the compiler, we saw that actually we could teach the compiler a lot of category theory. And then beyond category theory, you can actually teach the compiler a lot of math. So a lot of, I don't know, stuff that you know from math, that this sum is just, so this geometric series can be expressed just like that, right? You know, just as a quotient. And things started really to speed up significantly. David, you might have a question.
Oh, I was just going to let you know, you asked me to let you know when there was 5 minutes before. So
Yeah, wonderful. I'm close to end, by the way.
Yeah.
So the solution is compilation. What every compiler does. So when you have a stack of data structures in C, they will be called struct. I don't know what they're called in Julia. So usually you have structs and structs and structs. And what the compiler does, it really goes and deconstruct this nested structures. And what happens when you actually work with a tower is that you start with an input on the highest level. For example, this is now the category of finitely presented right modules, if you remember. And you see that now in the highest level, I have this co-kernel completion, and then I have to unbox it to get to the data, which are just opposites of matrices and stuff and so on and so on. And then I reach here in the ring, and then I'm doing just a ring multiplication or ring addition or something. And then I have to do everything back just to wrap my entire result, just to figure out that I have to unwrap or unbox everything again. Yeah. And this is the source of the overhead. But this is the stuff that compilers can easily get rid of. So it's not just CompilerForCAP. Any compiler does this actually by default. So the compiler just smooths these bumps like any compiler should do. But the idea is that we have this compiler now really in our hands. We develop the compiler, and we can teach the compiler completely high, non-trivial categorical logic that other compilers simply don't know about. You can also teach it mathematics and things that you find in the code that you see, oh, in this code, this expression is mathematically equal to this expression. This takes ages to compute. This takes a second to compute. Yeah. So this was a graphic by Kamal Salah when Fabian did his PhD student. So before Fabian did his PhD thesis, so before Fabian did his thesis, we were actually running into these bumps. And then came Fabian and developed the compiler. And now we can really, as if we're on the German highway. So it's really nice. So consider a computation in the categorical tower. So here is really a parametric problem. It's parameterized by the size of the matrix. So the problem size is 1, and you see actually almost no difference. The factor is 5. And if the size of the matrix is just jumps to 2, then the factor is 50, 250, 1,000, 5,000. And then here you would need to wait more than a week, and then you simply stop it. So this is actually what we're interested in. So we see the difference between finishes in seconds, and we'll never finish. But this also applies to languages where you do have a compiler. Yeah, because now it's not really about just a generic compiler. You really need a compiler which is aware of the mathematics you're doing. So CompilerForCAP can also be used for removing additional sources of overhead, so mathematical sources of overhead, for generating categorical code from categorical towers, as I showed you last time, as a proof assistant for verifying categorical implementation. So this proof assistant is really very simple-minded, but we used it to verify the implementation of additive closure. And I'm now collaborating with Benedict Arends from the TU Delft so that we have a collaboration between CAP and ROC, which was called COC in previous times. So the conclusion is that algorithmic category theory is a high-level programming language, and CAP is somehow a dialect. And of course, it can be redone in other systems. And using this language for building categorical towers allows us to reach a wide range of advanced and complex applications. So we don't have this nightmare problems when we think about new applications. And this allows reusability, separation of concerns, verifiability, and emergence in a substantial way. And this approach naturally comes with a computational overhead, but for this we developed the compiler, which can avoid this overhead and allows us to make this concept of categorical towers really fully usable. And thank you very much for your attention.
Thank you, Mohammed. That was excellent and perfectly timed. So now we have time for questions. We have about 10 minutes. If somebody in the Zoom has a question, raise your hand under the React button and I'll call on you, or you can just unmute if no one's talking. We have a question from Evan. So Evan, please.
Hey, Mohammed. Thanks as always. That was a really interesting, great talk. So I have a couple of questions about the use of like the linear relations. Is the utility there that like instead of say assuming that an inverse or a function exists, you can just sort of postulate some relation and later check that it has the right property? Is that why you're using that technique or?
Yeah, so the idea is that you know that of course relations are invertible. You can just
Yep.
flip the two, so you can realize this as some sort of span or co-span. It's equivalent, or as a triple, where you say that this is the idea of a generalized morphism, that actually a morphism, you know, the fundamental theorem of homomorphisms tell you that there is an isomorphism between a factor of the source. I think you say domain and not source. There is a factor, there is an isomorphism, natural isomorphism between a factor of the domain and a sub-object of the codomain, right?
Mm-hmm.
And if you want, you have to do the following. So you have to say my morphism starts by me first descending to a sub-object and then mapping, but not mapping to the codomain, but mapping to something of which the codomain is a factor object, a quotient object, right? And then you have really a symmetric situation. And this is something you can flip, but this is due, the insight is already due to Gauss, that this is the same as just taking the domain and the codomain and taking a direct sum and just taking a sub-object of the direct sum of the domain and the codomain. A relation which you can interpret in both directions. And everything what diagram chasing is telling you, that if you do this with relations, you end up having, again, an honest morphism. So this is one very nice interpretation or very elegant interpretation of diagram chasing. Go to the generalized morphisms or the category of linear relations, do the stuff, and then you will end up again with a genuine map or a genuine.
Yeah, and then at the end, check that you actually have a genuine map. Yeah, okay, thanks. A kind of more high-level question, I suppose, is it seems like the overall strategy for dealing with doctrines here is you know how to do the free construction for that kind of thing. You know how to construct the pre-additive category or whatnot. But then you also need to know how to introduce quotients, having done that. And I'm wondering how quotients are handled architecturally in the system. Like as you add on more layers, at each step, your existing equalities will imply more things. And so how does that fit into the architecture of your system?
Very good question. It's really an excellent question. So very down in the ladder, the quotients, for them you really need a normal form algorithm, something like the Grosvenor basis or the Hermite form, something like this. And then there is something I didn't talk about called the homomorphism structure, which I just used at one place to compute morphisms between two objects in my category. So this also helps you if
we seem to have lost you, Mohammed, for a second.
Mohammed, I don't know if you can hear us, but you are muted somehow.
You don't have an algorithm to decide.
Sorry, Mohammed. You were muted or somehow inaudible for about 30 seconds. So
I didn't mute myself. So shall I talk again?
Yeah. Can you just try again? Thanks. Yeah.
Yeah. So At the very bottom, you have things like Grosvenor bases that give you normal forms. And you can pull this up to some extent. One way to pull this up is something called the homomorphism structure, which I had no time to talk about. But you cannot do wonders with it. So
Yeah.
I don't know how to take quotients of abelian categories, right?
Right.
I can just work locally and do things locally, but some stuff is impossible. So if I'm taking a quotient with respect to a Serre category, and I know this Serre category is localizing, then I can again decide equality of morphisms. So it really depends on what kind of quotients I'm doing, right?
That makes sense. Yeah, thanks.
Yeah, you're welcome.
And you mentioned hi Mohammed, you mentioned the
Yeah.
low down in the tower that you have some normal forms, but I guess if you go too far down to plain categories, of course, you also aren't going to be able to take arbitrary quotients and decide
Yeah.
equalities, right?
Yeah.
So it's
Yeah.
really
And
searching for.
some stuff is simply undecidable. If you work with a general ring and then you take a quotient, then there is no Grosvenor basis algorithm, and then you're lost. I mean, you run simply into the word problem. So sometimes you lose at the very beginning, but sometimes it takes deciding equality of morphisms. But still, even if you cannot decide equality of morphism, you can still go on, right? So nothing in this approach really. So I would say maybe 99% of the computations don't really bother to check if two morphisms are equal or not. And the equality of objects is something else, right? Category theory is exactly the flexibilization of the equality of objects, right? You can all like in type theory, right? And make really the equality of morphisms to be the hard part. Yeah, I know my answers are not satisfactory in general, but of course you're happy to also send me emails and we can discuss about specific constructions.
Great, thanks, Kevin and Evan. Mohammed, if people want to either use your stuff or help develop it or something, like, is there a pipeline for either of those for people to get onboarded in either capacity?
Yeah, of course. So if you Google the Homalg project, you should get to the main GitHub parent page, under which we have the old Homalg project, but also the new CAP project. And you can click on CAP and you see the packages which are CAP-based and actively developed. And you see also the doctrines which we have predefined. And of course, there is a lot to do. So I'm busy till the end of my life. So we have a lot of to-dos, and there is a stuff we want to expand CAP in a lot of direction. The only limitation is simply time.
Great.
Yeah, so people could just reach out to me directly or to one of the group members, and you can go from there.
Cool. I have a technical question that I'm not sure is a good one, but when I think of a doctrine as like a two-monad on cat, this is a more general question than just for you, but I'm just going to ask it anyway. You want opposites to always exist or something. Like, is there any interest in, like, I mean, is there anything to do with the opposites at the level of the doctrine that means that you'll be able to take opposites or anything like that?
I'm really using the doctrine in the sense of structured categories. Just for the lack of a name. I know that this may be the historically first use of doctrine, and now we'll use it in a more general way. But as you saw from the constructions here, without the opposite, we have to double the work or quadruple the work even. And actually, we had categories and their opposite when we started. And you know what you would do if you don't have the opposite? You will go and copy the code, paste it, and then modify it, and then run into hell. Yeah, because you will never modify it correctly. So this was really our biggest concern. So without the opposite category, the entire philosophy of Tower will really be not so useful. Yeah, but it's in the sense of structured categories. So there is one doctrine that doesn't have an opposite, which is elementary topos. just because of lack of time. So I should at some point sit down and define is elementary co-topos, and then define what are co-exponentials. I think we have co-exponential, but we don't have factor object classifiers. So we also need factor object classifiers and so on. And then the opposite will work nicely with toposes. So you can dualize toposes and get co-toposes and with their internal logic.
Well, let's all thank Mohamed again for a great talk. And I'll turn off the live stream and all the other things, recording. And